So you remember when we were talking about generators and how they work, that we said, well, we have this loop of wire that's in a magnetic field, and this loop turns as if I move this loop of wire in this magnetic field, it would generate a current. But if I flip it over by 180 degrees, then the current switches direction. And so when we were talking about these generators, we said, well, there has to be some way to change the direction of the current. And it actually changes. We use these special switches, kind of like what y'all use in lab. There's double pole, double throw switches that flip the direction of the current. Similar to that, they do the same purpose. Where each time it rotates around by 180 degrees, it changes so that the current flows in the opposite direction. So with AC electricity, you just don't have that switch, so that each time it flips around, the current then will switch the direction, will change direction. And that's how you get alternating current. You just don't have those switches. And so if you look at the current, then if I were to plot the current versus time, if I don't have those switches, it'll oscillate back and forth. So it goes back and forth from some maximum to some minimum, and everything in between. The use of this, or the great thing about this, is it allows the use of step down and step up transformers. This, meaning AC electricity, allows for the use of step up and step down transformers. We'll get into this later in this chapter towards the end, right before the exam, and so you'll probably see some questions on this. But a step up and a step down transformer is basically, you just have two coils of wire like this. I have one current coming in, and then I have another coil of wire like this. And when the current in this coil of wire changes, it causes a magnetic field, right? If I have a changing magnetic field caused by this coil of wire, it's going to induce a current in this coil of wire. Remember our EMF, by the law of induction, which we've already seen, says that the induced EMF is equal to negative d phi dt. So this coil of wire will cause a changing magnetic field. Not just a magnetic field, but a changing magnetic flux. And then that magnetic flux then will induce an EMF in this second coil. And when you induce that EMF, you can have it so that the voltage is either bigger or smaller. If it's bigger, that's called a step up or step down transformer. What am I doing to the voltage if I go from a smaller voltage to a bigger voltage? I'm stepping it up, right? So that's where those things come from. If I'm going to a smaller voltage, like I do on those transformers out on the street, they go from 3,000 to about 120 volts. Or even those bigger transformers like at those substations, where I'm going from 10, 20, 30,000 volts from the primary lines down to about 3,000 volts. Those are step-down transformers. We'll talk about how these work, but this is the basic idea. But we'll also look at how they work later in this chapter and actually be able to calculate either the induced EMF or the EMF required to get a certain voltage. All right. Now, for our AC electricity, we describe the EMF in this way. It's pretty important. Our EMF is equal to our maximum EMF, our amplitude. So it's called our amplitude of our function, times the sine of omega d times t. This omega d is the driving angular frequency. Physically, this is set by what? This says how often does it oscillate. It's our angular frequency is 2 pi times the actual frequency. But physically, as we're generating the electricity, what is that set constant driving frequency? Right, how fast the thing spins. So that is directly linked to this angular frequency, how fast that coil spins. We have this coil in a magnetic field, and then that sets what our angular frequency is. All right. So this is omega d is directly related to how fast the coil spins. EM is the amplitude. It's also, we think of it as the maximum EMF, or the maximum voltage. So if I plot my EMF as a function of time, it looks like this. EM will be either here, that would be negative EM, or up here, that's going to be positive EM. So it's just your amplitude of this wave function. And then I can also give the current. We'll see that the current, when we get into some different functions, we'll see that the current doesn't always follow this function, that it's sometimes out of phase. And so we're going to write this in this way, that the current I is equal to our amplitude, that's our maximum current, times the sine of omega d, that's our driving angular frequency, times t minus some phase constant. So this phase constant will be fairly important, and we'll figure out some ways to actually calculate what is this phase constant. The phase constant describes how the two waves are associated, or how they're related to one another. We're dealing with oscillatory functions here. These are trigonometric functions, sines or cosines we typically deal with, sines usually. But they don't always have to be in the same phase. So imagine that if I have two functions like this, and the peaks line up with the peaks and the troughs line up with the troughs. These are said to be in phase, and if they're in phase, then phi is equal to 0 degrees. However, if they're out of phase, have you ever seen phase constants like this? Is that a trick question? Is that what you said? Oh, in trig, yeah. Is that a trick question? All right. You can also have waves that are out of phase. So imagine here if I have a wave that's like this, and then I have, well, you know, in waves we have a wavelength. Right, one wavelength, that's one wavelength. If I offset the next wave, the second wave, by a half a wavelength, so let's see, if I offset the next wave by a half a wavelength, it's gonna do, I'm gonna have it look like this. What is a half wavelength? There to there is a wavelength, so it's gonna start right here. Yeah. So this is offset by a half a wavelength. And we say that this has a phase angle of 180 degrees. Hopefully this will make more sense when we get into phasors, because these angles you'll see sort of physically what they mean. But this just says how are these two waves oriented with respect to one another. If one of them is offset, then the two waves have a phase angle. If they're both in line, so that the peaks line up with the peaks and the troughs with the troughs, then they're in phase. Yeah. Yeah, everything on this test will be in radius. All right, even though you'll, listen, on the problems, if you have to be in degree mode, I'll tell you. I'm going to have in the instructions very clearly. I'll make very clear on this test. Okay, and I'm going to hold my questions too. So this would either be 180 or pi, right? All right. By the way, you get destructive interference. I don't know if you dealt with light. Are you seen light before? Yeah, of course you've seen light before. But you get a point when you have waves, like if you were to add up these waves, if you were to add these two waves, when the peaks line up with the troughs, you would just get no energy at all. They would destructively interfere when you added them up. All right, you see this, for example, with sound waves. You'll have the noise canceling headphones. You might have that. Yeah, so you know how those work?
No.
Well, they have a microphone. Your noise canceling headphones, they have a microphone that gathers all the outside ambient noise, and then it shifts that wave function by 180 degrees, so that it shifts the whole thing over by 180 degrees, and then it puts that sound, that shifted wave function, into your headset, so that it cancels out with all the ambient noise. Right, so it takes, say it reads this wave function. Now, noise is going to have a lot more complicated wave function. Whatever the function is, it reads that, and then in real time it offsets it by a half a wavelength. It gives it a 180 degrees phase shift, shifts that wave function over, and plays that into your headset. And then it cancels out with the two wave function, and you get nothing at all. It's actually pretty cool. It seems complicated, but it's pretty simple to do.
So like in a wave, like a wave of light, if you did actually offset it at half a wavelength, you would basically be in darkness.
Right, yeah. Let's see, you're engineering, so you probably won't see it again, but the chem majors will have seen double slit diffraction. Right, I've done double slit diffraction. Or diffraction gratings. Yeah, with diffraction gratings, they use that property. That's why you get spectral lines, because of this interference of light. You might see it again if you take another E&M class. Anyway, all right, so let's look at forced oscillations. That's just when we're hooking up an AC electric source to a circuit that oscillates. So forced oscillations. In LC and RLC circuits, the charge, voltage, and current oscillated at a frequency given by the circuit. It's as if, the circuit had some natural frequency. We called that, if you recall, that omega was equal to the 1 over square root of LC. For our LC circuit, remember we had the capacitor and the inductor, and they switched energy back and forth, and it did it at a very regular rate. And that rate that it did it, switched these energies back and forth with this 1 over root LC. Remember, it's like the spring the mass on a spring. It switches energy back and forth at a very regular rate. And with a mass on a spring, that's set by the spring constant. But in this case, it's set by the value for the capacitance and the inductance. So it has a natural frequency. But when you hook it up to a driving frequency, to an omega D, if you hook up if you connect this circuit, an RLC circuit, or any combination of those, a resistor, an inductor, or a capacitor, to an AC source, the oscillations always occur at the driving frequency. And the driving frequency, remember, that's that omega D, which is set by the rate at which that coil of wire rotates. Right, so you have this natural frequency, this omega equals 1 over root LC, but then when you ever hook up this circuit, you get you get this driving frequency. Now there is some resonance, like if you have this operate at this frequency, if our AC circuit operates at an omega D that's equal to 1 over root LC, we'll see that that's when you get a maximum current out of the circuit. We'll get to that probably next week. But whenever you have a circuit, it's always going to oscillate at this omega D. That's our driving frequency of the source. Now, let's look at 3 circuits. They're all pretty simple, but they can seem a little complicated. All right, so 3 circuits. The first one is just an AC electric source. I'm going to use this symbol for AC electric. This is like our battery that we have for direct current, but now I'm driving this alternating current. I have a resistor, and that's it. This is my EMF. It's driving an EMF in that direction. I also know that I have, this is my resistor R, and I have a voltage drop across this resistor, which I'll call VR. Alright, I know from the loop rule that E minus VR, that this is equal to 0. That's just from the loop rule. That still holds true. Like all the circuit stuff that we did with DC circuits, it's going to hold for AC circuits as well. And if you've taken a more advanced circuits class, you'll see all those things as well. So, since I know that this is EM, that's my maximum, times sine omega dt, right? That's just our EMF for a driving AC electric source. Then I can define VR as equal to this EM sine omega dt. I'm going to use a little v here. This just refers to the voltage at any particular time. So if I were to plot out the voltage, the maximum would be this VR here, where this is the maximum value. But this little lowercase v is just going to be the voltage at a particular time. Right? So it's as a function of t. All right, I could also write this then as VR is equal to big VR times sine of omega dt. This is just the voltage across the resistor, and this is the maximum voltage across the resistor. I can also define I, and that's what I really want to get to for all these circuits, is some function for I. And so this is pretty simple by Ohm's law. The only thing that's complicated is I now have this sine function. I'm going to use a lowercase I. That gives the current as a function of time is going to equal to VR divided by R. So that's going to be VR divided by R, which is, excuse me, this should be little VR. VR sine omega dt divided by R. Let me just step back for a second. This is our circuit, right? The power supply and resistor. And so just like we've seen before, it's a pretty simple circuit. It just has, you can think of it as a battery, but it's a battery that changes with time. So I can write my loop rule like this, that the sum of the voltages across a closed loop has to equal 0. That's just the loop rule. And my voltage across the resistor is still going to be negative. Then my voltage here, which is a function of time, this is the voltage across the resistor, is given by this, because I know that VR equals this. Okay. So whatever voltage I have on the resistor, I'm also going to have on the power supply. Those are going to be equal. And so my VR here, this is just rewriting this and just saying, well, the maximum EMF that I get across the power supply is also the maximum voltage drop across the resistor. And then I can make a function for the current, just by Ohm's law, because current is V over R. Put in this function for V over R, and I get a function for the current. I can further write this, since this VR over R is just my maximum current. I can say that my current on the resistor is equal to I max, my amplitude, times sine of omega dt. Okay, so you'll have this on your equation sheet. Let's see, you might also have this. I'll get your equation sheet out soon so you can be looking at it. And I'll say this is for, you know, a circuit with a resistor and a power supply. All right. I want to draw the function, and I'm going to show you what phasors are, and we'll do some problems. You're going to have some phasor problems that's asking you to interpret phasors, but once you see them, they're pretty simple. All right. So if I were to plot E or VR, it will look like this. Say it starts at 0. Remember, my function for VR is equal to big VR times sine omega dt. Okay, so I started at 0 because sine of 0 is 0. This axis right here is my t-axis on the x-axis. Then if I want to plot I, I'm going to plot I here in red, and we actually lowercase I. What is my current at the very beginning? Where at this point, at t equals 0, what is my current? Is it going to be some maximum value? Is it going to be 0, or is it going to be some minimum value at the very beginning? It's going to be 0. It follows exactly the voltage. Whatever the voltage is, then the current is going to follow it. So if I start here at 0, is my current going to go up or down from there? It's going to go up because the voltage goes up, right? Will the voltage reach the same level as the, or excuse me, will the current reach the same level as the voltage, or will have a value that's less than the voltage? It'll be less, right? Because the current is V over R. So assuming that R is a you know, the current will be less. All right, so my current now follows a function that looks like this. We say that these are in phase, by the way. So the phase constant, phi, is equal to 0. All right, so I can, I'm going to show you, I'm going to draw a phasor diagram. I'm going to take a point right here. A phasor is just a vector. Is a vector that rotates around the origin. The magnitude of the vector is equal to the amplitude of the function at that time at a particular time. It's going to rotate in a counterclockwise direction. At a rate omega d. That's the frequency, the driving frequency of my AC electric source. Right. The y component of that vector will show the magnitude of the function at that time. So the y component of the phasor, or of the vector, or excuse me, the amplitude of the function at that time. Let me just show you some examples. It's sort of hard to describe in words, but let me show you an example. So here I'm going to draw some phasors. These are just vectors, and we're going to deal with them like vectors like we did in last semester. But I'm going to draw a phasor that represents the blue line here. All right, so here I'm going to take an instant in time at this point, and I know that my amplitude here should be positive or negative. It should be positive, right? And is my amplitude, as I move forward in time, is my amplitude increasing or decreasing? It's increasing. So I'm going to draw my phasor for that point in time as being right here. Right. It's just a vector. It starts at the origin and it goes up from the origin. The amplitude then, this is my phasor for VR. The amplitude is given by the y component. So whatever this y component of that phasor is going to be the amplitude of the function for VR that I have. Can I erase this text here? Okay, I'll wait a second. Now, what if I pick this point? Where am I going to draw my phasor? Where am I going to draw my phasor on this diagram to represent this point in time? And remember, these phasors, they're going to rotate around this axis. They constantly go around this axis as I proceed in time for this function. So how is that phasor going to be drawn for a point over here? Now notice that my v is positive or negative at this point? It's positive, but it's decreasing. So where am I going to draw my phasor over here? In which quadrant will I draw? That's right. Well, just don't worry about the angle. It's going to be in quadrant 2. All right. So if I pick another point, say over here, I'm going to draw the phasor for it over here, because I still have a positive value, but it's decreasing. Because say if I come down here, I'll draw a phasor there, and now notice that my amplitude, which is the y component, has decreased. And if I get to this point, let's see, can y'all see yellow? Yeah, you can sort of see yellow. At that point, where is my phasor? It's going to be on the x-axis. On which x-axis? The positive or the negative x-axis? Negative x-axis. Very good. So at that point, yeah, it'll be on the negative x-axis.
It's still decreasing?
Because it's still decreasing. Let me show you. I have a little website.
Like the next intersection is 0, they'd be on the positive x-axis because they're increasing.
That's right. Let me show you an animation of this. Alright, yeah, so here's our function. This one is tracing out a sine function. Yeah, it's pretty cool actually, a way to show how this trigonometric function is traced out. Alright, so if we notice, say, at this point, it should be right up here, right? Because that's at my maximum, the y component. At this point down here, it should be here. Let's see. Yeah, it is there, because I have a negative maximum. At this point over here, it should be right here. Yeah. You'll have a question on the test, and then the homework I'll have one to practice, for you to practice, interpreting phasors. Because it's pretty important when we get into RLC circuits. Phasors allow you to do very simple calculations to determine what is the function of the current for an RLC circuit, which could otherwise be a complicated calculation. But with these phasors, it makes it just really simple. Okay. So back to this. I'm going to erase this text now. If I want to draw the phasor for I and V, how are they related to one another? That is I in the same direction as V, or does it precede or follow behind V? What do you think, Hunter? That's not what you said just before. Okay. The current is always going to be the same way, because if we look at the functions for the V and the I,
yeah, they're the same.
They're the same. Yeah, where is it? I thought I had that. What's that? Right, they're in phase, right. So see, these are in phase. That means the phase angle is always 0. So they're always in phase. So if I were to draw my phasor, say for a particular time, I'll do this time right here. I'll draw it. The blue phasor, which is VR, would look like that. And then the red would be IR. So this would be IR, and then this would be VR.
So it's the same position, just like a different length, like shorter?
It's shorter, right, because my current.
That's why it says follow behind. I didn't.
Oh, okay.
Yeah.
I was confused.
Okay. No, it's always going to be, so as you follow these through, let's see, I think there might have been a simulation on this website. I never understood phasors. Okay, well here's two phasors that are not in phase. Let's see, are there two? No, there aren't two that are in phase. But it looks just like this other one, except you just have two arrows going around at the same time.
That makes sense. If I is equal to V over R, then I will always have to be smaller than
Right. Mm-hmm. Alrighty? Okay. Like I said, I never understood phasors until like yesterday, so hopefully y'all understand it better than I do. But you'll see with an RLC circuit that it makes determining the current very simple. And you will have a phasor problem, both interpreting phasors, and then when we get into RLC circuits, having to determine what is the current by looking at the phasors. But once you see them, they're pretty simple. Alright, so that's our one circuit. Let's get into this next one, or let's do a sample problem. You could also just see a simple calculation like this. Say I have a circuit with an AC electric source and a 200 ohm resistor. Let's say that the maximum amplitude is 36 volts, and my driving frequency, this is not the angular frequency, this is the actual frequency, is 60 hertz, which is what we have in our country. Different countries have different frequencies, but in the US we have 60 hertz, which is why you have to get converters when you go to Europe or wherever. Alright, so that just means that that coil of wire rotates 60 times a second, and that's what sets up our driving frequency. Alright, so I want to know a couple of things. Yeah.
That was really quick for a second, 60 rotations in a second.
Yeah, that's pretty fast. They go pretty fast.
Why is Europe different than the US?
I don't know. I'm sure there's a reason, but I don't know. They just like to be different, I guess. Is that why? Okay. I don't think it really matters. I don't think there's a big difference. But all right. So what is? I want to know a couple things. What is the function for VR of t? And then I also want to know. You'll need to know this actually. Is what is the amplitude? That's that big VR for that function. And of course, we'll also need to know omega d. All right. Let's find omega d first. So omega d is equal to the how is it related to the frequency? We multiply times what? No. Okay, remember frequency is in 1/seconds, but omega, angular frequency, is in radians per second. So you just want to multiply how many radians there are in a circle times that. How many radians are there in a circle? There are 2 pi, right. So my omega d is just equal to 2 pi f. Alright, so that's going to be 2 pi times 60, that's just 125. I've learned I tell you I'm taking Greek. I'm taking Greek, and my Greek professor pronounces it not pi, but pi. I don't know if that's like more Greekish or whatever, but that's how he pronounces it.
More Greek.
So we should start calling it pi, but then we'll get it confused with, pi. So, alright. I learned the Greek alphabet. Do y'all care? Do you want to hear it?
Yeah.
They have a song. I don't know if I can get the tune right, but it's Alpha, Beta, Gamma, Delta, Epsilon, Zeta, Eta, Theta, Iota, Kappa, Lambda, Mu, Nu, Xi, Omicron. Yeah, Nu. She messed me up. Nu, Xi, Omicron, Pi, Rho, Sigma, Tau, Upsilon, which is my favorite Greek letter, Upsilon, Phi, Pi, Psi, Omega. That's the end of the alphabet. Alright, so Omega d is 120 pi. VR here, what is my VR equal to? Not complicated. What is my VR? This is the maximum. Let me go and write the function for little VR, which we know to be, as a function of t, is equal to VR times sine omega dt. You'll have that function.
It'd be sine omega dt over, it'd be under little or VR, right? You divide both sides by sine.
No, I just want to know what is this value. This is a certain value. This is my maximum voltage. What is it?
Oh, 36.
It's 36, right. So that's just my maximum voltage. So this is equal to 36 volts times sine omega dt. And that's it. We have the function. All right, so I have VR of t is equal to 36 times sine of 120 pi t. And of course, this is in radians. All right, your calculator needs to be in radians whenever you do this. All right, so for example, I could say, well, at t equal 1 second, what is VR? All right, can you find that for me? I don't know what it is right off. What you got, 1.4? Somebody confirm that? I don't know. Let me just double check. If you don't mind me. So I have 36. Oh yeah, it's 0. All right. So here my my voltage is 0 at t equal 1 second. V is equal to 0 volts. That means that it's occurring where? Like if I look at this function. Right, it's hitting the axis somewhere along here. So, all right.
So then you like increase the time, or
Increase the time? No, don't worry about it.
But that should be when it's ascending, but like when it's increasing.
Why do you say that? Oh, right. You're right. Yeah. So this is a factor of 2 pi. That means
121, it would be going down, but because it's even, it's going up.
right. You'll see what he's saying. That the sign.
Okay, on my calculator, I'm getting 1.44
Did you put in 120 pi, or did you do 120 times 3.14?
I put 120 times
Oh, I don't know. When I put in my calculator,
Yeah, very, very.
so let's say,
If I put that, it would be the same, that's what it would have.
yeah, basically like 1, 0, 0, 0, 0, 0.
I don't know why, but it can be accurate.
All right. Yeah, so let's make that point as well. So V equals 0 when omega dt is a function, or is a what's the word? A multiple of pi, some integer times pi, 2 pi or 1 pi. All right? Or 2 pi or 3 pi or 4 pi. All right, our next circuit, I'm just going to write the function here. I have a few more minutes. Will be very similar, but our circuit number 2 will be an EMF source with a capacitor. So here I have my capacitance. The voltage across the capacitor will be the same as the EMF, VC sine omega dt. That's going to be just like the driving force, the EMF source. And my charge on the capacitor, which I'll call QC. Let's see, what's the charge on a capacitor equal to? The maximum charge? We have charge, capacitance, and voltage. How are they all related? Right, CV. So this is C times, I'm going to call this little VC times sine of omega dt. We'll pick that back up next time, and we're going to derive the current, and we'll do the phasors for this as well. See how the current lags the charge and the voltage on this. Let me go. Can I go and write out the function? We have 5 minutes. If it's okay, I'd like to go ahead and get this going. So I know that current is dq dt. So if I want to know this function for current, I just take the derivative of my charge here. I have this function for the charge, so that current is d dt of C VC, or excuse me, this is my maximum current because it's the amplitude, times sine omega dt. What's this equal to? Well, omega d is just a constant, so I don't take the derivative of it. That doesn't have a derivative. I just take that constant out. All right. So yeah, you're right. It's going to be C VC times the derivative of this thing, right? But the derivative of this with respect to d is just omega d, right? Times cosine omega dt. And that's it. We're going to define something here called the impedance. I can write this now as VC over XC times cosine of omega dt. Here X is called actually the, what's it called? The capacitive reactance. Sorry. You can think of this sort of like the resistance. This is sort of like the resistance that the capacitor does. It's like the resistance. And we'll treat it like a resistance next time. So it makes the calculations a little more easy. And XC is equal to 1 over omega DC. See, I'm just putting this in